Alright, so we've got these two particles and we're given their velocities, v1 being 6 plus 2t, we're in meters and seconds, and v2 being 4 minus 2t, so meters per second. So if I want the displacement of this particle, I'm going to have to integrate. So if I integrate, this will be 2t squared on 2, so and then plus c. This one will be 4t minus t squared plus c. So in order to find that plus c, I need some more information, and there we get given the information initially. So when t equals 0, we are given that x1 is 2, that's particle 1, and x2 is 1. So if I use that here, I've got 2 equals c, and over here I've got 1 equals c. So my x1, my particle, is actually 6t plus t squared plus 2. And my second particle is 4t, this is its displacement, so they would both be in meters. So if I want the distance between them, d being x1 minus x2, I'll just do that. So I've got 6t, take away 4t is 2t, okay, I didn't write it down, but that's okay, t squared minus t squared is 2t squared, and then 2 take away 1 is 1. So that's the difference. Now, if you look at the discriminant of that, because that's clearly a quadratic, and you know, if I put it doesn't really matter if I put it in order because both coefficients of a and b there are 2. All right, so discriminant b squared, so 2 squared, minus 4ac. So you can see we're going to get a negative 4, so it's less than 0. And we know when the discriminant is less than 0, there are no real solutions. So the distance between them, the difference really is never going to be equal to 0. It can't be equal to 0. So they never meet. They never ever meet. And if you think about it, if we look at this kind of description for the distance between them, or the difference between them, we know first of all that time is always going to be greater or equal to 0. So these are going to get bigger and bigger and bigger, and further away from distance being 0. So really, at t equals 0, the distance is 1 meter between them, and that's going to be our minimum distance between them. So yeah, all right. So now, if we want the midpoint, so let me rub that out. We don't need that anymore. Plus 2 and plus 1. Just remember that. Whoops. Alright, plus 2 and plus 1, there we go. So yeah, if I wanted the midpoint, let's just call it M. Really, what am I doing? I'm just adding these two displacements over 2. That would be giving me my midpoint. So if I add them together, I've got a t squared minus a t squared, that's 0. I've got a 6t plus a 4t, that's 10t. And I've got a 2 plus a 1, so that's plus 3 over 2. So that would be the midpoint. Now, if I was looking for, find its distance, hang on, it's moving with constant velocity. All right, so that is the midpoint, as in the displacement of the midpoint. So if I wanted the velocity, I would differentiate to get the velocity, which you can see would be 10 on 2 or 5. So it's going to be 5 meters per second. So you can see it's going to be constant. It's not depending on time at all. So that midpoint is moving at a constant rate, constant velocity there. All right, and then we want to find its distance from each particle after 3 seconds. Well, clearly, if I look at that after 3 seconds, where is that going to be? That's going to be 33 over 2. So our m is going to be 33 over 2. Our x1, if I sub 3 in at time equals 3, I'm going to get 18 plus 9 plus 2, just using that equation with 3 in it. And my second equation, I'm going to get 12 minus 9 plus 1, just putting 3 in that equation, so that's going to be 4. So if I have a look at, well, the distance between x1 and m, I have 29 minus 33 on 2. So I'm going to get 12.5 or 12.5. If I do the same thing with the second point, that was 33 on 2, 16.5. So I'm going to get 12.5 meters. they will be the distances.